Okay, well, I guess with that we'll get rolling. So thanks everybody who's here and everybody who's watching virtually. We're pleased to have speaking today, but displeased that she's unfortunately wasn't able to make it. Lindsay Cooper, who is an assistant professor for now at the University of California, Santa Cruz. That was a positive for now, not a foreboding for now. Um, um, where she studies PL-based approaches to building concurrent and distributed software systems. I'll also mention she received her PhD in CS here in 2015 with Ryan Newton. And she also is a co-founder and organizer of Bang Bang Con. It's a kind of eclectic computing talk series that ran from, I think, 2014 to 2024. Yeah, and also the recipient of the Career Award, an ICFP Distinguished Paper Award, and a Google Faculty Research Award. So anyway, very pleased to have here Lindsay Cooper, and go ahead, take it away. Thanks.
All right. I think we checked that I'm audible earlier, so hopefully you can all hear me. I'm so happy to be giving this talk, so thank you, Carlo, for hosting and for that lovely introduction. So I'm going to talk about research, but this is much more than just a routine research talk. There is personal significance for me to be giving this particular talk to this particular audience, and I am only sorry that I couldn't be there in person to visit Bloomington, where it's so beautiful in the fall. So I'm going to begin, as I so often do, with a little bit of storytelling to set the stage. And the story has to begin with Dan. So I was a PhD student here at IU from 2008 to 2014. And when I arrived in 2008, I took Dan Friedman's programming languages course, which was fondly known as Intro to Dan. And in this course, you learn about what programming languages are made of by writing interpreters. So that was how my PhD began, and it was how I got hooked on programming languages as a field. So I was at Indiana for 6 years doing a PL PhD, and that journey involved a lot of twists and turns. And that would be enough for a whole other talk. But long story short, eventually I was working with my advisor, Ryan, on programming language abstractions for writing shared memory deterministic concurrent programs. And we published some papers about this line of work using what we called monotonic data structures. And it was all about shared memory, or so I thought. But then in the last year or so of my PhD, people who were interested in distributed computing, so specifically not shared memory, tracked me down and said, hey, your work seems to have a lot to do with our work. You really ought to read our work. So as an example of that, here's an email I got in 2013 from Mark Shapiro. So he's a well-known distributed systems researcher, and he's one of the inventors of something called conflict-free replicated data types, or CRDTs, which are data structures that are used in distributed systems to ensure fault tolerance and high availability. So I got this email from Mark near the end of my PhD, and you don't have to read this, but this is essentially pointing out that I ought to be paying attention to his and his collaborators' work on CRDTs because it had a lot to do with my work. And it turned out, of course, they were right. So, of course, to make sense of CRDTs, I had to do some background reading on distributed systems. And one thing kind of led to another. And, when I started looking at the papers that these folks were recommending to me, it was kind of a revelation for me, since up until then, I had only really paid attention to programming languages as a subfield, and I didn't really look beyond PL research to consider everything else out there. But once I did finally look beyond PL, I realized, wait a second, I realized distributed systems are actually fascinating. And the field of distributed computing is something that I had a lot to learn from. So not only is it immediately practically relevant to our work and our lives, but it's also full of profound and beautiful results. And so that's when I really began to study distributed systems. And so, of course, I haven't stopped being a PL person. PL is still my research home. But for these last 10 to 15 years, I've attempted to study distributed systems from a PL person's point of view. And I was going pretty slowly at first, right? But this learning process accelerated quite a bit when I got a job at UC Santa Cruz in 2018. and I was suddenly expected to teach distributed systems courses. So at that point, it really meant I couldn't fake it anymore. I had to actually deeply understand something about distributed systems instead of being a dilettante like I had been. And so that in turn influenced what research problems I was interested in. And so these last several years, that's mostly where my mind has been research wise. And my students and I have been going around sneaking distributed systems papers into PL conferences. So these papers listed here are a few examples from the last 6 years, a couple of which I'll say more about later. But finally, then, after many years of this, at some point recently, I had another revelation. And this one is not going to come as a surprise, to someone like Dan, or really to any of the people here who are part of the Dan Friedman intellectual tradition, which I like to call the Dan aspera. And of course, that includes a lot of you. And that revelation, of course, was that it was actually about interpreters the whole time. So despite having been on this sort of long side quest into distributed computing all these years, it turned out that a lot of what my students and I had been doing all this time was still all about interpreters and interpretation. So, oops. So in the rest of this talk, I'm going to discuss a couple of our group's projects that exemplify this realization that I had. And both of these projects are about distributed systems, but I'm going to talk about them through the lens of interpreters. So of course, this obligates us to try to answer this question of what is an interpreter? So by the way, I would like this to be interactive if possible. So, for those of you who are on Zoom, feel free to put peanut gallery comments in the chat. They won't be a distraction to me. In fact, I enjoy it. So I'm interested in people's takes on, what exactly is an interpreter. What exactly is an interpreter? Well, let's see what the dictionary says. And this is actually a shout out to Ken Sean, who, when I asked on Mastodon what an interpreter is, he helpfully sent me this dictionary definition, which is someone or something that interprets. Well, okay, thanks. That's not actually very helpful at all. Okay, so there's another definition that's more computing specific. So let's see what that one says. Okay, there's actually two definitions here. So one is a machine that prints on punch cards the symbols recorded in them by perforations. Okay. And the other is a computer program that executes each of a set of high-level instructions before going to the next instruction. Okay. Well, you tried. I think this definition is pretty bad also. I think we can do much better than this. Okay, so how am I going to define what an interpreter is? So for the purposes of this talk, I'm going to say that an interpreter is something that takes syntax and produces semantics. And I like the generality of this definition. So it lets us plug in domain-specific notions of syntax and semantics for whatever domain we care about. And it doesn't even have to be computing specific. So for example, and this analogy is due to my friend CF, we can think of a choir as an interpreter. So I'm a choral singer myself, and this analogy makes a lot of sense to me. It's the choir's job to interpret a musical score, usually aided by a director who, for the purpose of this analogy, we can think of the director as part of the choir. So it's their job to interpret the score and ultimately produce some audible music. In computing, we might think of an interpreter as something that takes a program and produces a value. So I'm using the word value here, but I'm using it pretty loosely because that sounds very pure and like there aren't any side effects. But a program might well have some sort of effect on the world. I'm not even going to attempt to define program here, except to say that both this notion of program and this notion of value might be domain specific. And I'll also point out that the value that you produce here might even itself be a program. In which case, what is this last arrow on this slide? Well, now it's actually a compiler, right? Because you're taking a program and you're producing a program. So, at risk of annoying Jeremy and the other compiler folks here, I'm going to argue that for the purposes of this talk, a compiler can be thought of as just a special case of an interpreter. And I would also argue that every programming language is interpreted because sooner or later your code will be executed by the CPU, and a CPU is itself an interpreter. So it's interpreters all the way down. And there's one last really important thing that I want to mention about what interpretation means. So if you will continue to indulge me with this choir analogy. So a music score for a choir is typically going to have different parts, right, that different people sing. So if we say that syntax is interpretable, then that usually is going to connote something about the form that that syntax takes. In particular, it'll say something about how the interpretation of a given input has to be determined by the interpretations of its subcomponents. And the result you get is compositional. So to be able to do this, there has to be an obvious way to break down the input into its subcomponents and put them back together. And in other words, it has to be inductively structured data, like an AST. So what I want to do next is dig into a couple of specific places where this idea of interpretation seems to have arisen in my own work in these last several years. And so I'm going to focus on two projects from that list that I gave earlier. And those are library level choreographic programming and causal separation diagrams. I'm going to talk about both of these things, and I won't really have time to do more than just scratch the surface of either of them. But I'm really happy to dig into the details more in Q&A or chat with folks later. So let's jump in and let's talk about library level choreographic programming first. Okay, so let's talk distributed systems. So in the world of distributed computing, we're usually concerned with message passing. And the idea here is that you have some independent nodes that communicate with each other via a network, and they do it by sending and receiving messages. And they don't share memory, so the only way for them to coordinate with each other is by passing messages like this. And you might be able to imagine having some sort of so-called distributed shared memory as an abstraction on top of this, but under the hood, it's ultimately all message passing. So let's suppose that our independent nodes are Alice and Carol. And there's typically some kind of global behavior that we want here. And Alice and Carol have to together accomplish that, but they have to do it by only taking local actions. So the only thing that either of them could do is send messages or receive messages or take internal actions. So if we want to run a really, really simple protocol in which Alice sends a request to Carol and Carol responds to Alice, how do we program that? Well, we can assume for now that we have some sort of send and receive functions that actually implement the message transport somehow. So it might be TCP, it might be HTTP, it might be pigeons flying around. Let's not worry about the details of how the transport layer is implemented. And let's just think about what Alice and Carol have to do, assuming it exists. So for this protocol, Alice would run this node local program here on the left, and it might look like this: send a request to Carol, and then wait to receive a response from Carol, which gets stored in this variable here. And meanwhile, Carol is running her own node local program, which might look like receive request from Alice and store it in this variable request, then do something to handle the request, and then finally send a response. So this is just about the simplest distributed program that I could conceive of. But even in this really simple program, notice how Alice and Carol are utterly dependent on each other to faithfully follow the protocol. So for instance, if Carol neglected to call receive over here, now that's become Alice's problem. So Alice will now wait forever to get a response. Or what she might do is time out and report an error, depending on how send is implemented. So in general, in a distributed system, nodes have to execute messages in this very careful dance where a message sent from a node has to be expected by some recipient and vice versa. So if somebody's running buggy code, then things go wrong for somebody else. And it only gets more complicated if we add nodes. So let's say that Alice is sending Carol a request, and then Carol is supposed to pass the request along to Bob and then get an acknowledgement from Bob and finally respond to Alice to acknowledge her request. And this is the sort of pattern that you might see, for instance, in primary backup replication, where let's say Alice is the client, Carol is the primary, and Carol gets a request from Alice, which she then has to pass on to Bob. Bob has to act Carol, and Carol has to act the client. So in this scenario, Alice might not even know that Bob exists. But nevertheless, if Bob is misprogrammed somehow, then that could mean bad news for Alice. And in fact, this example brings to mind this wonderful quote from Leslie Lamport, where he defines a distributed system as, quote, a system in which the failure of a computer that you didn't even know existed can render your own computer unusable. So the challenge then for programmers is to try to reason about the behavior of this distributed system, the implicit global behavior of this system, while writing the explicit local programs, which are just sends and receives and internal actions that actually run on the nodes. So this brings us to choreographic programming. And the idea of choreographic programming is let's make that implicit global behavior actually explicit in the code. So in choreographic programming, we don't write the local programs at all. Instead, we write a single global program that's called a choreography. And then we generate a collection of local programs, one for every node, from the choreography using a technique called endpoint projection. So what we have on the left here is a choreography that expresses the protocol that we talked about earlier. So every choreographic programming language is going to have some sort of operator like this highlighted squiggle arrow here. And this is usually pronounced com because it denotes communication between two parties. So looking at this first line here in the choreography, a com expression is going to express both a send and receive at once. And what this means is that Alice computes this value request, communicates it to Carol, Carol receives it and stores it on her end in the variable x. When this choreographic program gets projected, every time you have an occurrence of Alice on the left-hand side of a com like this, it's going to turn into a send call on Alice's node. And every time you have an occurrence of Carol on the right-hand side, that's going to turn into a receive on Carol's node. So thanks to this way of writing code, as long as our endpoint projection is correct, we can rule out the possibility of a mismatched send and receive. And we can therefore rule out a certain kind of bugs that could occur in our collection of local programs that we end up with. And so in a nutshell, that's the benefit of choreographic programming. So I do want to acknowledge one of the elephants in the room, which is that with what we've shown so far, choreographic programming per se doesn't actually do anything to help us if one of these nodes should crash or if one of these messages should be lost. So those fault tolerance problems were present in the non-choreographic version of the code, and they're still present here. So choreographic programming doesn't do anything to fix that as such. What it does do is rule out programming errors that stem from a programmer not calling send where they should or not calling receive where they should. So in a simple program like this, that might not seem like such a big deal, but once more parties are involved, it becomes less simple. And it's in that multi-party setting where choreographies really shine. So next, let's look at a setting with 3 participants and with some more interesting control flow. Okay, so this is a slightly more interesting protocol. Suppose that Alice wants to interact with Carol, but Bob stops her to check her credentials first. So this example is kind of like a sign-on through a third-party authentication service. And by the way, this example is straight from the choreographic programming zine that my student Ali and I wrote last year, which you can get from my website if you want. And in the zine, it's Alice that wants to go to Carol's birthday party, but she's stopped by the bouncer, Bob. In this protocol, Alice has to have her credentials verified by Bob before she can interact with Carol. So Alice sends those credentials to Bob. Bob runs this check function on Alice's communicated credentials. And then depending on the outcome of that, Alice will either get an access token from Carol or not. So this diagram represents 2 different ways that an execution might go. So how do we express this in a choreography? Well, in a choreography, we can have conditionals at the choreography level. And here's what that looks like. So on the first line, here's our squiggle arrow again. And this notation, alice.credentials squiggle arrow bob.auth request means Alice is computing something called credentials and then sending it to Bob, who receives it and then stores it on his end in this variable called auth request. And then we have a conditional. So the conditional check takes place locally on Bob's node. And then depending on which branch we take, either Bob communicates success to Carol, who then communicates the token to Alice, or Bob communicates failure to Carol, and then Carol tells Alice that she can't have the token. So what I think is useful to point out about this execution is that even though the execution is spread out across these three different parties, so this is a distributed execution, but if we think about this execution globally, this is actually a sequential program in which steps happen one after the other. And we can see that from reading the choreography. The choreography just looks like straight line code. And in fact, the choreography looks remarkably similar to our informal diagram that we drew. So if we were to write this code as a traditional distributed program, which is really three programs running on the three participants, then the control flow wouldn't be as obvious. So having it as a choreography actually helps the readability of the code as well. Okay, so to actually run this thing, we need to do endpoint projection on it. So endpoint projection will take this choreography and it'll project it to these versions that are running on Alice, Bob, and Carol. And this is done automatically by the choreographic language implementation. And I've written some pseudocode here to give an idea of what the projected code might look like. And notice, like I said, in this projected code, the control flow isn't as clear. You might have to stare at it for a bit to figure out what's supposed to happen first, what's supposed to happen second. So choreographies give us this readability advantage. There's some stuff that I'm leaving out here. One important side note here is that when you do endpoint projection, if the choreography had a conditional like this, then the parties that are involved need to be told what branch to take. And this is called the knowledge of choice problem. And different choreographic languages have different ways of dealing with this. So for instance, if I hadn't had code in my projected code that communicates the outcome, or if I didn't have code in my choreography rather, that communicates the outcome of this check auth request call, then some choreographic languages would then complain that the choreography is what we call unprojectable. And other languages would just insert the necessary communication code for you. So that's all an interesting problem in its own right. And if you're interested in knowing more about that, then I'm happy to talk more about it later. Okay, so now you know what choreographic programming is. So we didn't invent any of this stuff. Choreographies have been around for a long time. And dating back to the early 2000s, there was something called the World Wide Web Consortium's Web Services Choreography Working Group. And they developed a draft specification for a language called WSCDL, which stood for Web Services Choreography Description Language. However, this wasn't intended to be executable. It was only a specification language. You couldn't actually run these things. So fast forward to 2013, when there was a language called Core developed by Marco Carbone and Fabrizio Montesi. And this pioneered the idea of an executable choreographic programming language that used endpoint projection to compile choreographies to these runnable node local programs. And then in 2020, Fabrizio Montesi teamed up with Saverio Gianlorenzo and Marco Perissotti to create the Choral programming language. And Choral is intended to be useful for realistic programming, and it's notable for how it uses mainstream object-oriented programming abstractions. So it's designed to be familiar to, say, Java programmers, and the Choral compiler projects choreographies to executable Java code. Then in 2022, Andrew Hirsch and Deepak Garg created a choreographic language called Pirouette, which combined choreographic programming with higher order functional programming. So this paper made a splash in the functional programming research community, and it won a distinguished paper award at Popple that year. And this is how my students and I found out about choreographic programming for the first time. And this paper, by the way, is also notable for its mechanized proof of deadlock freedom. So my student, Gan Shen, read this Pirouette paper and decided he wanted to try implementing a choreographic language himself. And so, being who he is, the approach that seemed obvious to him was to do it as an embedded domain-specific language in the form of a Haskell library. And the idea is really straightforward. And what's funny about this is that Gan wasn't even trying to do something novel. He just wanted to learn about choreographies. But it turned out, to our surprise, that this idea of implementing a choreographic language purely as a library had not been done before. And this appeared at ICFP 23, where it also won a Distinguished Paper Award. So for a couple of years in there, every paper about choreographic programming in PAC and PL was getting a Distinguished Paper Award. Sadly, no longer true. So let's dig in a little bit and talk about Haskell and how it works. So I'm going to contrast this with the traditional approach to choreographic programming, which is exemplified here by Choral. So in Choral, you write a choreography in the standalone Choral language, and you compile it to executable endpoint code using a standalone compiler. So Choral compiles to Java, and then you can run those Java programs using the usual Java toolchain. And this all works fine, but it means that you need this purpose-built language and this purpose-built compiler. So in Haskell, on the other hand, and this is our framework, choreographies are expressed as programs in an existing host language. In this case, it's Haskell. And the choreographic language constructs and endpoint projection are all implemented entirely in this host language library. So there's no additional compiler support needed, no additional runtime support beyond what the host language can already do. So in particular, our choreographic language is implemented in Haskell as a DSL using something called a freer monad, which separates the interface and implementation of effectful computations. So by itself, this language doesn't actually assign any meaning to the choreographic operators, like that squiggle arrow that I was talking about before. Instead, it just accumulates them as this big term, and then we dynamically interpret that term based on the location where the code's being run. So, for instance, that squiggle operator, if you're a sender, that gets interpreted as send. If you're a recipient, that gets interpreted as receive. And if you're anyone else, then it's a no-op. So all the usual benefits of embedded DSLs apply here. So because these programs in Haskell are really just Haskell programs, that means that a Haskell programmer can take advantage of the whole Haskell ecosystem. They can use their existing Haskell tools for development and debugging. They can use other Haskell libraries, and they can compile it just like any other Haskell program. Whereas for something like Choral, it's a whole new language, right? And you might not have any tooling unless the developers bother to implement it. And there's one other plus side, I think, to this embedded DSL approach, which is that it makes it easier to integrate choreographies into bigger non-choreographic systems. So there's no need to change languages just to implement certain pieces as choreographies. And I think this is really important because while choreographic programming might be a good fit for certain components of a program, there might be other parts of the program where trying to fit it into that choreographic paradigm just doesn't make sense. So maybe you have a program where almost all the code happens locally, but maybe there's like a short-lived network interaction just to do authentication or something. So then, it wouldn't really make sense to have to write everything in a choreographic language just so you could get the benefit of choreographies for that one little piece. So that's an argument in favor of this library level approach. And one of the consequences of this is that endpoint projection actually happens dynamically at runtime. So let's take a look at the type of the endpoint projection function in Haskell, and I hope to convince you that this is really just an interpreter. I promise you that this is the only line of Haskell code that I'll make you look at in this whole talk. So endpoint projection is a function that takes two arguments. The first argument is this choreo thingy here, which is a choreography. So endpoint projection takes one of these choreographies. And the second thing that it takes is a location, which is the place we want to project the choreography to. So like Alice or Bob. And endpoint projection returns something called a network, which you can think of as a low-level program in terms of sends and receives that's been specialized to the location you gave as an argument. So for the Haskell enthusiasts here, both choreo and network are freer monads, but you should think of them both as just being programs. And these choreographic operators that are in the choreo programs all get interpreted to things like send, receive, and broadcast in the network programs. So choreo gives us a syntax. On the network side, I've put semantics in quotes here because this isn't actually semantics, it's still just syntax. And then that will get dynamically interpreted to the actual meaning of send and receive and so forth. The actual meaning of send and receive and so forth is going to be supplied by a network backend. And Haskell comes with two of those that you can choose between. There's an HTTP backend, which uses HTTP for the network transport. And there's a local backend, which implements these send and receive functions as communication among threads on a single machine. So that's endpoint projection. It's just an interpreter. So returning to our timeline of choreographic programming, it's really exciting how since Haskell came out in 2023, a bunch more choreographic languages as libraries have popped up. So there's a bunch more new choreographic programming libraries in these last 2 years. Some of them are from our group. So Multicore is a successor to Haskell. Chorus is a choreographic programming library for Rust. ChoreoTS is a choreographic programming library for TypeScript. But what's even more exciting to me is that a bunch of these are not from our group. So there's CoreCamel for OCaml, there's CoreX for Elixir, there's Chlore for Clojure, there's Coret for Racket, and there's Unicorn, which is for a distributed programming language called Unison. So all of these are doing dynamic endpoint projection. So endpoint projection at runtime, just like Haskell. But they all do it using the idioms that make sense in those languages. For instance, Coret is built on top of Racket, and in Coret, it's done using macros, which is super cool. So all of these different approaches use the idioms that make sense in the languages that they're implemented in, and I love that. All right, and then here I've just given the GitHub URLs for a couple of our projects. So here's the Haskell repo, and then here's the repo for Chorus, which again is our choreographic programming framework for Rust. So feel free to take a look at these and check them out. This is work led by my students Gan Shen and Shun Kashiwa. And then Chorus was also the lead author on it was Mako Bates, who is a recent PhD graduate from Joe Neer's group at University of Vermont. Okay, so that's it for the first line of work that I wanted to talk about on library level choreographic programming. And now I want to talk about causal separation diagrams. So let's talk diagrams. So people who work on concurrent and distributed programming have been using diagrams like these. I call them Lamport diagrams, but they're also known as sequence diagrams and time diagrams and a bunch of other names. People have been using diagrams like these at least since the 1970s as a way to try to wrap our heads around how concurrent and distributed systems work. I've been using them throughout this talk, and they're pretty intuitive. I didn't have to explain what these diagrams mean, and you might have drawn one yourself on a whiteboard recently. These diagrams depict the events of interest in a system, usually things like when messages are sent and received, and the relationships between those events across space and time. And these diagrams are so intuitive that we see them at all levels of academia and industry. But they are just pictures, right? They're not formal objects, but they could be formal objects. So if we want to reason formally about executions, like what's the one that's shown here, we need a formal model of executions. So let's talk about how to do that. And I'll put the diagram on the left here and this textual formalism on the right, but these are really expressing the same information. So the first thing we would need is a collection of processes, right? These are modeling whatever locations are participating in the system. And then every process is going to have a sequence consisting of the events that occurred on it. And events could be message sends, or they could be message receives, or they could be events that are internal to a process. So we have a sequence of events on each process that's totally ordered. And then last, we're going to have pairs of events that comprise messages, which is where information propagates from one place to another. So here, for instance, A1 would be a local event on this process P1. A2 would be a message send event, and the message is being sent to P2, where the receive event is A5. So what I'm showing here is a completely standard way to formalize executions, and it gets used all the time with good reason. But it does have some pitfalls. So what are some of the problems with doing it this way? So one issue is that this representation doesn't stop you from representing something that's actually physically impossible, like a causal loop. So here, um, uh, A2 is the send event for this message, A5 is the receive event, and then later on process 2, we have a send event for a message that's being sent backward in time back to P1. So this is an execution that couldn't actually physically happen. And the structure of our data doesn't really help us avoid this situation. The formalism will still let us write down this execution that couldn't actually occur. And you would need to do some additional checking to make sure that your data is self-consistent. The other problem is that this representation doesn't stop you from representing what are called inconsistent cuts. So a consistent cut in an execution like this is something like this blue line with a happy face here. It's separating the events of the execution into a clear past and a clear future. So here the past is what's above this blue line and the future is below it. And if an event is on the past side of the cut, then if it's a consistent cut, then everything that's causally before that event is also going to be on the past side of the cut. And so this blue cut is in fact a consistent cut. An inconsistent cut, an inconsistent cut like the one that's represented by this red line here fails to have that property. So here, for instance, we have this event A5, which is on the past side of this cut, but A5 represents the reception of a message that was sent here at A2, which is actually on the future side of the cut. So A2 should causally precede A5, but A2 is on the future side of the cut. So the traditional model doesn't help us avoid inconsistent cuts. And so if I just take a prefix like this of the events on each process, well, it might be a consistent cut or it might be an inconsistent cut. And the problem is that there's no connection between the processes that we're splitting into past and future and the messages that we need to respect. So you might have heard of this famous software development dictum, make illegal states unrepresentable, which I think is due to Yaron Minsky. And as my student Jonathan put it, this way of representing executions makes illegal states all too representable. Okay, so what do we do about this? What should we do instead? So to get a better idea of what's problematic about the traditional approach to representing executions, let's take a closer look at it. So here I've written down the same execution that we were looking at before. I've turned the diagram on its side and kind of flipped it around, and I've removed the labels on events, but it's the same execution as before. It's got the same structure. The only difference is that I've added some additional dotted gray and dashed blue lines to this diagram, which make the structure of the execution more explicit. So in this traditional approach, the top level structure of this execution is this collection of processes. So the first thing we have to do is visually separate these processes from each other. And that's what these dotted gray lines do. And we can think of them as spatial boundaries between the processes. And next, each of these individual processes has a sequence of events in time. And we can make that explicit too by adding these dashed blue lines as temporal boundaries between events. Unfortunately, we cannot really do the same thing with messages. Because we made the order of events within a process our top priority, messages are kind of a different kind of entity. But notice how these message arrows always seem to cross these gray spatial boundaries, which run horizontally. They cross those rather than crossing the blue temporal boundaries, which run vertically. So these process local edges that cross over the dashed blue lines are inherently causally ordered by the structure of the data. But the edges that cross over the dotted spatial boundaries between processes are not inherently causally ordered by the structure of the data. And that is what makes it possible to accidentally construct an inconsistent cut. So this happened because we prioritized the spatial boundaries first instead of prioritizing the temporal boundaries. What would happen if we did it the other way around? What would happen if we laid down the temporal boundaries first and then the spatial ones? That's exactly what our approach does. So here's that same execution again, but now represented using one of our diagrams, which we call causal separation diagrams. So it's the same execution, but represented in a different way. First, we're laying down enough consistent cuts to separate every event. That's what these vertical dashed blue lines are. So instead of splitting up by processes first, we're splitting up this execution into these global time steps, where by time I mean logical time. And then within each of those global time steps, we can add these spatial boundaries between each distinct location. And we end up with this different way of decomposing our diagram. So the original way of decomposing it, we had this structure that consisted of these three separated sequences of events. In our new decomposition, we have a single sequence, not of events, but of global steps. And then those global steps, which are these columns here, delimited by these dashed blue lines, those are each made up of local steps delimited by the spatial boundaries. So here we've got four big global steps arranged from left to right, separated by the blue dashed lines, and then every global step happens to contain three local steps, separated by these gray dotted lines. So this choice to prioritize the temporal boundaries over the spatial boundaries is the fundamental difference between our approach, CSDs, and the traditional model. And everything else is just a consequence of that. And I've been saying temporal boundaries, but I could also just as well have called them causal boundaries, because this potential causality here is following the flow of time, hence the name causal separation diagrams. And what's most interesting here is that both messages and processes now evolve over causal boundaries. Information never crosses directly over a spatial boundary. And as a consequence of that, a diagram that can be decomposed this way necessarily has no causal loops. In other words, if we can construct diagrams this way with a CSD, they are necessarily going to be causal by construction. So we have made illegal states unrepresentable. Here are all the different kinds of local steps that we can build diagrams out of. In the first two here, a tick is just a local event on a process, and a no-op is the absence of an event. These last two, swap and a sock here, they don't model any actual events. Instead, they just allow us to rearrange the wires through the diagram so that processes can communicate with more than just their immediate neighbors. And you can think of these as sort of like structural rules in a logic. And the middle two, fork and join, these are modeling the two halves of a traditional message. But unlike in a traditional message, we have both the process and the message state that are coming out the right-hand side, rather than having the message go out the top or bottom. So in fact, our model doesn't distinguish process state from message state at all. Nothing prevents a so-called process from joining state with another process, or stopping a local event from occurring on a message. So we're referring to these inputs and outputs uniformly, not by processes or messages, but by sites. A site is just a place where state can exist. And this was my student Jonathan's innovation. And it took me a while to get my head around treating messages and processes as the same thing, but it actually makes sense to me now. So a process sending a message is just a site forking off a piece of its state out into the world as a new site. And a process receiving a message is just two sites joining together. So now that we have these tiles, these composable tiles, we can stick them together however we like and get a consistent CSD. And I've left it out here for brevity, but each one of these tiles actually has a type, which says how we're allowed to compose it with the other tiles. And we also have combinators for composing local steps into global steps and for chaining global steps together into an execution. And the type of each tile tells you how it can be composed with the other tiles vertically and horizontally. And for the fancy type enthusiasts here, yes, these are dependent types. So what does all this have to do with interpreters, which is the topic of this talk? So earlier, when we were talking about what interpretation meant, I said that if we say that if a syntax is interpretable, that usually means that the interpretation of an input is determined by the interpretations of its subcomponents. And to do that, we need to have an obvious way to break up the input into subcomponents and put it back together. The obvious way to break things down and put them back together is what we call an induction principle. So for that traditional formalization of executions that I showed first, we unfortunately don't have a nice induction principle for the thing on the left here. We just have a set of processes and a set of messages, and the structure of the data doesn't tell us how we're supposed to break things down and put them back together. So executions that are represented in this traditional way on the left are not particularly amenable to interpretation, not if we want to work in a tool that encourages us to inductively define data structures, especially like a mechanized proof assistant. But on the other hand, executions that are represented as causal separation diagrams do come with a lovely induction principle, since they're actually just lists of global steps. So to take a CSD apart, you can just peel off one global step at a time. To put it back together, you can just glue on one global step at a time. And this makes CSDs amenable to interpretation. So CSDs give us a formal, graphical, inductively defined syntax for representing concurrent executions. And it's something that we can straightforwardly write interpreters for. So that's exactly what we do. So in our paper, we talk about 3 ways to interpret CSDs. That is 3 ways of giving CSDs a semantics. So the first one of these is an interpretation of CSDs into what we call causal paths. And causal paths are nothing but a proof-relevant analog of the classic Lamport happens before relation. So instead of just saying that 2 events are causally related or aren't causally related, we can interpret a CSD into a dependent type of the causal paths through a diagram. And these paths give evidence of the causal relationship between events. The second way that we interpret CSDs is into logical clock functions, which assign an event to its corresponding logical timestamp. So there are a lot of different kinds of logical clocks that get used in distributed system implementations, Lamport clocks, vector clocks, matrix clocks. Our interpretation is parametric in a choice of clock implementation. So you can instantiate the same machinery over many logical clocks, and we've done that for a bunch of different flavors of clocks. And the third way that we give to interpret CSDs is into proofs that clocks respect causal paths. So a logical clock that respects causal paths is a clock that satisfies Lamport's clock condition, which is the thing that makes a logical clock a logical clock. So using CSDs, we're able to give a mechanized proof of the clock condition that's parametric in the choice of clock. And this interpretation-based approach to verification of clocks would be really awkward and difficult if we didn't have this inductive data structure that accounts for causality. But since we have CSDs, it just kind of falls out naturally. So to wrap up this part, I'll just mention that you can find our proof development on GitHub. This is done in Agda. And my student Jonathan and I are actively looking for more things to use CSDs for, which I'd love to talk with folks about. Okay, so we're almost at the end. So to sum up, I've talked about 2 lines of work from my research group that turned out to be all about interpreters all along. So we talked about library level choreographic programming, which lets programmers write distributed programs as single unified programs in their favorite language, and then dynamically project them to multiple endpoints. And we talked about causal separation diagrams, which are inductively defined data structures designed for elegant mechanized reasoning about happens before relationships in concurrent executions. But really, we could sum up these 2 lines of work as being about interpreters. Haskell is just asking, what if endpoint projection was an interpreter? And CSDs are just asking, what if you could write interpreters for Lamport diagrams? So the takeaway I have for you here is you can't go wrong by studying how interpreters and interpretation works. And then go study something else, and you can reap the benefits of applying your knowledge to that new domain. So that's all I've got, and I want to thank you for your attention.
Great. Thank you very much. There was some applause you may not have been able to hear. Any questions from the audience here? Yeah. Jeremy.
Hey, Lindsay, awesome
Hi.
talk. On the causal separation diagrams, can you also like interpret them just into like behavior, like to run them? Uh,
Yeah, that's a great question. Yeah. So, yeah, I mean, in principle, you can interpret them however you want, right? So a CSD, I mean, what your question kind of, implies is like, is a CSD a program that you can just run?
yeah,
And
yeah.
so for the CSDs that we have, a CSD just represents a single execution, right? It's representing like one execution. Um,
Oh, okay. I guess I get it.
but actually, we would like to have CSDs that represent programs, right? Because, in the end, like we really want to think about programs. And so CSDs should actually like, so what would make it a program? Well, it would have to have control flow, right?
Mhm.
It would have to be more than just a single execution. And we're actually working on that. So we're working on like extending CSDs to kind of do more, and then a bunch of cool stuff follows from that. Like if you can represent entire programs or protocols with CSDs, then you could run them, or you could uh, or you could um, verify them, or do lots of other stuff with them. So yeah, stay tuned.
Very cool. Thanks.
Okay, well, maybe I'll ask a question. So, going back to Haskell, is
Yeah.
it a problem that I guess every endpoint has to be running, has to have the whole program? Um,
Yeah, that's a terrific question. Okay, so the question is about with Haskell. Um, so uh, we're taking this kind of weird approach to choreographic programming, right? Where unlike something like with choral, right, in the traditional approach, you're projecting to these individual programs, right? And then every endpoint just gets its individual piece, right? So there are settings where you might really need that, right? Like maybe it's a security problem to have every endpoint get all the code. Whereas with Haskell, you're putting the one program on every node, right? The one choreographic program on every node, and then every node is dynamically projecting it to what they need it to mean for them. So if you have code that you can't distribute to everybody for whatever reason, then the Haskell approach as discussed here isn't going to work for you. So people are kind of actively working on how can you take code that's written this way, right? Like how can you take something that's implemented using the library level Haskell approach, but actually do this static endpoint projection with it. So there has been like a little bit of progress on that question, both from my group and from another group. So there was one paper um, at at the Haskell Symposium last year called Welcome to the Partitioning, which was about static partitioning of programs, including choreographic programs written using Haskell. And they were able to do it. They did have to, they had to involve a compiler plugin. So it did involve some compiler support. So it used a GHC plugin. So that's getting a little bit away from our, purely library level approach. But, that's if that's what you need, then that's what you need. And then we had a paper just this year. This was in collaboration with Yao Li at Portland State and his student Grant Van Domelen, which was about, well, if we use an abstraction other than freer monads, if we use something called freer arrows, which is a little bit more statically analyzable, then that should give us a way to do this endpoint projection statically. And so we have a prototype of that, which appeared just in last month at the Haskell Symposium. And so this is something like how to combine the strengths of the standalone language approach with the library level approach is something that people are actively working on. But your question is a very good one, because like this question of like what if you don't want to give all the code to everybody, whether it's for security reasons or for I don't know, intellectual property reasons or whatever, then this dynamic interpretation approach may not work for you. So people are trying to work on how to combine the strengths of these two approaches, and yeah, stay tuned on that as well.
Okay, thanks. Yeah, I mean, I'll just add one comment that since you're saying everything's an interpreter and the word projection is appearing on all these slides, I can't help but think like maybe it's a, Futamura projection, question mark, uh,
Yeah,
end of comment.
so I that's a great question. And, I was nervous that somebody was going to ask me something about Futamura projections for this talk, because it is a talk about interpreters. And so, I'm just going to kind of enthusiastically wave my hands in response to that.
Great. That was the spirit of the question. Yeah. Anyone else? Okay. Ken?
Hi. This is great. It's beautiful. CSDs are new to me, so it's extra beautiful to me. So maybe two questions about CSDs. First of all, so I'm sorry I haven't read your paper. It's certainly not your ACTA code, but like, is there like an equational theory? Because it feels like there are different ways to, you can do swap swap, and that should be
Mhm.
equal to identity or something, right? And
Yeah, that is such an astute question, Ken. Thank you for asking. So the question is, so with the traditional approach, there's kind of like one way to write there's one way to express an execution in this representation per execution. But unfortunately, that's not true for CSDs. So for a CSD, there's lots of different CSDs that might correspond to a particular execution. Basically, depending on where you draw these horizontal lines, I could split up this diagram in different ways. So a given execution might have a bunch of different decompositions as a CSD. So Ken's question is, do you have an equational theory? Like, how do you know when one CSD is equivalent to another CSD, right? In the sense that they represent the same execution. And so, well, I mean, what we have is a few ideas that are kind of ad hoc, right? Like we know that certain like if you do like swap, or if you do like, I don't know, like fork followed by swap, or maybe that's a bad example. um I don't know. We know that some of these tiles can move around in certain ways. I guess I'll put it that way. But we don't have something like fully fleshed out. And yeah, I mean, I wish we had something like, like a proper sort of like notion of equivalence for CSDs. And I think you could come up with one. We just like haven't actually written it down yet. I think that would be a really useful thing to have. And yeah, collaborators welcome.
yeah, thanks. There are students present. And the other question is, I also haven't looked at your proofs. So
Mm.
are they graphical? Are your
Ah.
Agda proofs similarly graphical? Because that would be cool.
Yeah, that's a great question too. So we have like there's actually two different syntaxes for CSDs. There's the graphical syntax and there's a textual one. So the textual one just looks like tick, join, fork, swap, et cetera, et cetera. And so uh and we also have like in Agda, we have something that sort of tries to be the graphical syntax, but it doesn't look quite as good as it does on these slides. Um, but you can express CSDs using either the graphical or the textual syntax. And most of the time, when we're writing code on a computer, we use the textual syntax because it's what's convenient. Um, but um, but it would be nice to have like some better tooling for that.
Cool. Yeah, thanks.
Hi. Yeah, since last time you came here, I read the booklet. I have this question in mind for a while. And I guess this is a question following Carlos' question. Uh,
Mhm.
so, yeah, so for example, if so the code, in my understanding, is someone has to write that and distribute that to multiple different nodes. What if one of them wants to modify the code and
Mhm.
then tribute that to everyone?
Yeah, that's a great question. So the question, to repeat the question, is so in the Haskell approach, um, you're giving out this choreographic program to all the participants, and all the participants are running it and projecting it to their own node. But what if somebody wants to make a change? So yeah, Haskell doesn't really have a lot of support for that situation as such, right? Like you can't. and if somebody were to do that, then you would lose all the nice, guarantees of deadlock freedom that you would get from choreographic programming. So Haskell doesn't do anything to help you in that situation, and you would have to be very careful about it. And other nodes might have to modify their code too, which is kind of the whole problem that choreographic programming is meant to help you solve. So you do have to like kind of make this decision up front about how to design your code. This is actually a kind of a challenge that needs to be addressed if choreographic programming is to be made practical, right? Like how do we distribute code changes? And when somebody's code changes, how do you ensure that the parties that need to find out about the change find out about the change, and that nobody else's code changes, so that the change is minimal in some sense. I think this is actually kind of related to that question of knowledge of choice, which I brought up earlier. So it's a good question, and I think today the choreographic programming community doesn't have a great answer for it yet, but it's definitely something to think about. So thank you for asking.
Thank you.
Okay, Tianyu?
How I'm a little curious about the expressiveness of choreographic programming. So have you ever like implemented a realistic distributed protocol like Paxos in Haskell?
That is a great question. So Paxos specifically, no. However, there's
Or Rust?
actually a paper that that a friend of mine just submitted recently, which is about implementing consensus protocols using choreographies. So I need to take a look at it because I'm super curious about that. I think Paxos in particular is tricky for a couple of reasons. So one is that obviously there's the fault tolerant stuff, which I brought up before. So choreographies don't do anything to help you with fault tolerance. And you really kind of need to solve that. That's like kind of table stakes for wanting to do consensus protocols. The other thing is that in a protocol like Paxos, there's this notion of majority, right? Like a node can like receive
Like the
messages
leader
from
election,
any majority of acceptors, right?
Yeah.
And so you would need to be able to express in your choreography that you don't care who the messages are coming from as long as they're coming from a majority. And so you would need to have, something in your choreographic language that let you express that mechanism.
Right.
And so people are actively working on this.
Okay.
And I would actually recommend, so there's the group at UC Berkeley and also now at AWS that works on the Hydro framework. So their framework is like kind of choreographic, or at least they would describe it that way when they're talking to choreographic programming people. It's and so they've been able to implement consensus algorithms using their Hydro framework, which is really cool. And so the especially cool thing about it is that when you think about consensus, it's really useful to be able to think from this sort of global perspective, right? And so because that's how we think about how the protocol works, is thinking from this global point of view, right?
Exactly.
And so that lets you kind of, so Shadaj Ladad, who is one of the developers of Hydro, gave a talk about it here recently, and he talked about how, when you think about something like Paxos, you really want, instead of splitting it up by, proposer and acceptor and so on, you really want to split it up by phases, global phases, right? And that's how you want to, that's how you want to split the code up into components. And Hydro actually lets you do that. It lets you, your components can be like global phase 1 and global phase 2 instead of, splitting it up by participant first. So I really love that. And I think there's a lot of promise to that approach. I will say that like Hydro is, so it's not necessarily going to look like traditional choreographic programming in the way that I presented it here. But I still think it's worth looking at as being kind of, in the spirit of choreographic programming. So take a look at it.
Great. Yeah. Thank you. Any other question? Okay.
Hello, good talk again, by the way. I wanted to maybe ask more of a probing question about the uh let's see, what did you call it? The tiles that
Mhm.
you mentioned were typed to tell you how they
Yeah.
fit together. And you
Yep.
maybe even mentioned dependent
Mhm,
types
mhm.
as well. Um, Maybe you didn't want to talk about that too much originally, but I was just curious if you could say some more about that.
Yeah, I can. So, yeah, so each of these tiles has a type, and the type essentially expresses something about what happens at these boundaries, at these left and right boundaries of the tiles. So, so fork, for instance, can be thought of as a function that goes from one site to two sites like this. And so the type of fork expresses that and these things on the either side are called site configurations. So fork has to take a site configuration that has one site and it has to return a site configuration that has two sites. And this site configuration idea is coded up in AGDA as a dependent type. And you can see more details about the types of things in our paper. But these types essentially put a lot of guardrails on how you can compose these different tiles together, and site configurations have to match up with each other in a certain way, so that like when you compose a whole diagram together like this, I literally wouldn't be able like to write a diagram that had I don't know, let's say I wouldn't be able to have uh, a process that that does like a causal loop, because it would actually be ill-typed. So types are helping us there in that way. And there's a lot more detail about this in our paper. But yeah, that's it's leveraging the amazing power of dependent types to be able to constrain how you can construct these diagrams.
Thank you.
Okay. Well, I think maybe with that we should let people go if they want to. But thank you once again, Lindsay, for a great talk. And
You.
yeah, well, hope you make it back to Bloomington sometime.
I hope so too. Thank you, everyone.